Welcome to today's space adventure, James Webb Space Telescope. The James Webb Space Telescope, JWST, is a space telescope currently conducting infrared astronomy. As the largest optical telescope in space, it is equipped with high-resolution and high-sensitivity instruments, allowing it to view objects too old, distant, or faint for the Hubble Space Telescope. This enables investigations across many fields of astronomy and cosmology, such as observation of the first stars, the formation of the first galaxies, and detailed atmospheric characterization of potentially habitable exoplanets. The JWST will offer unprecedented resolution and sensitivity from long-wavelength, orange-red, visible light, through near-infrared to the mid-infrared, 0.6 to 27 micrometers, and is the successor instrument to the Hubble Space Telescope and the Spitzer Space Telescope. The James Webb Space Telescope was launched on the 25th of December 2021 on an Ariane 5 rocket from Kourou, French Guiana, and arrived at the Sun-Earth L2 Lagrange point in January 2022. The first Webb image was released to the public via a press conference on the 11th of July 2022. The Webb telescope was formerly known as the Next Generation Space Telescope, NGST. The telescope is renamed after James E. Webb, who was the administrator of NASA from 1961 to 1968 during the Mercury, Gemini, and Apollo programs. The U.S. National Aeronautics and Space Administration, NASA, led Webb's design and development and partnered with two main agencies, the European Space Agency, ESA, and the Canadian Space Agency, CSA. Webb's primary mirror consists of 18 hexagonal mirror segments made of gold-plated beryllium, which combined create a 6.5 meter diameter, 21 feet, mirror, compared with Hubble's 2.4 meters, 7 feet 10 in. This gives Webb a light collecting area of about 25 square meters, about 6 times that of Hubble. Unlike Hubble, which observes in the near-ultraviolet and visible, 0.1 to 0.8 m, and near-infrared, 0.8 to 2.5 m, spectra, Webb observes a lower frequency range, from long-wavelength visible light, red, through mid-infrared, 0.6 to 28.3 m. The telescope must be kept extremely cold, below 50 K, minus 223 degrees Celsius, minus 370 degrees Fahrenheit, such that the infrared light emitted by the telescope itself does not interfere with the collected light. It is deployed in a solar orbit near the Sun-Earth L2 Lagrange point, about 1.5 million kilometers, 930,000 miles, from Earth, where its 5-layer sunshield protects it from warming by the Sun, Earth, and Moon. It will study every phase in the history of our universe, ranging from the first luminous glows after the Big Bang, to the formation of solar systems capable of supporting life on planets like Earth, to the evolution of our own solar system. Initial designs for the telescope, then named the Next Generation Space Telescope, began in 1996. 2 concept studies were commissioned in 1999, for a potential launch in 2007 in a $1 billion budget. The program was plagued with enormous cost overruns and delays. A major redesign in 2005 led to the current approach, with construction completed in 2016 at a total cost of $10 billion. The high-stakes nature of the launch and the telescope's complexity were remarked upon by the media, scientists, and engineers. One of the James Webb Space Telescope science goals is to look back through time to when galaxies were young. Webb does this by observing galaxies that are very distant, at over 13 billion light-years away from us. To see such far-off and faint objects, Webb needs a large mirror. A telescope's sensitivity, or how much detail it can see, is directly related to the size of the mirror area that collects light from the objects being observed. A larger area collects more light, just like a larger bucket collects more water in a rain shower than a small one. Webb telescope scientists and engineers determined that a primary mirror 6.5 meters, 21 feet 4 inches, across is what was needed to measure the light from these distant galaxies. Building a mirror this large was challenging, even for use on the ground. A mirror this large had never before been launched into space. The Webb telescope team also decided to build the mirror in segments on a structure which folds up, like the leaves of a drop leaf table, so that it can fit into a rocket. The mirror would then unfold after the launch. One further challenge is to keep Webb's mirror cold. To see the first stars and galaxies in the early universe, astronomers have to observe the infrared light given off by them, and use a telescope and instruments optimized for this light. Because warm objects give off infrared light, or heat, if Webb's mirror was the same temperature as the Hubble Space Telescopes, the faint infrared light from distant galaxies would be lost in the infrared glow of the mirror. Thus, Webb needs to be very cold, cryogenic, with its mirrors at around -220 degrees Celsius, -364 degrees Fahrenheit. The mirror as a whole must be able to withstand very cold temperatures as well as hold its shape. Once a mirror segment's final shape is corrected for any imaging effects due to cold temperatures, and polishing is complete, a thin coating of gold is applied. Gold improves the mirror's reflection of infrared light. The desire for a large infrared space telescope traces back decades. In the United States, the Space Infrared Telescope Facility, later called the Spitzer Space Telescope, was planned while the space shuttle was in development, and the potential for infrared astronomy was acknowledged at that time. Unlike ground telescopes, space observatories were free from atmospheric absorption of infrared light. Space observatories opened up a whole new sky for astronomers. The first full-color images and spectroscopic data were released on the 12th of July 2022, which also marked the official beginning of Webb's general science operations. President Joe Biden revealed the first image, Webb's first deep field, on the 11th of July 2022. Additional releases around this time include Carina Nebula, young, star-forming region called NGC 3324 displaying cosmic cliffs about 8,500 light-years from Earth. WASP 96b, including an analysis of atmosphere with evidence of water around a giant gas planet orbiting a distant star 1,120 light-years from Earth. Southern Ring Nebula, clouds of gas and dust expelled by a dying star 2,500 light-years from Earth. Stephan's Quintet, a visual display of 5 galaxies with colliding gas and dust clouds creating new stars. 4 central galaxies are 290 million light-years from Earth. SNACS J0723.3 to 7327, a galaxy cluster at redshift 0.39, with distant background galaxies whose images are distorted and magnified due to gravitational lensing by the cluster. This image has been called Webb's first deep field. On the 17th of August 2022, NASA released a large mosaic image of 690 individual frames taken by the Near-Infrared Camera (NIRCam) on Webb of numerous very early galaxies. Some early galaxies observed by Webb like CEERS 93316, which has an estimated redshift of approximately Z equals 16.7 corresponding to 235.8 million years after the Big Bang, are high redshift galaxy candidates. The Hubble telescope can see the farthest galaxies, but the James Webb telescope will see the farthest stars. Thanks for watching. If you like the video, press the like button, subscribe our channel and press the bell icon to get the next video notification. See you in next space adventure.